Okay. Okay. All right. So what we're gonna do today is this. Having graphed systems of equations in the previous lessons. Today we're gonna do the second. All right, the second of the methods. Okay, because there are three methods total. So we did graphing. All right. The second method is called uh, something called substitution. All right, and then later on in the week we're going to do something called elimination. Okay, so yeah, let's see what substitution looks like. Okay, so today we're going to solve systems not from graphing. All right, that's the past few lessons. We're going to solve systems using substitution, okay, which is basically literal equations again. Okay, all right, so let's take a look. Now, I'm going to start off with the very, very simple substitution problems, and then as we go on, the kind of questions that we're going to use for substitution is more like what we did, like this. All right, this sort of stuff. Except we're not using, graphing anymore, right? Or this, right? Except we're not graphing anymore. We're going to use a algebraic method to solve it, not just by graphing. Okay, graphing is great, but graphing takes time. So let's see if there's a slightly faster way to do it. Okay. All right. Now, I'm going to start off with a very, very, very basic premise, right? And that is, okay, so let's say we have this question, right? And this is a system of equation because x equals 5. That's an equation, all right? And so is this one, right? This is just straightforward. So imagine, okay, again, if you were to graph this, right, x equals 5, which means, for every point of y, x is equals 5. So it'll be like 5, 1, 5, 1, 5, 5, 5, right? So 5 over 5 up, 5, negative 5. So you're going to get a line like this, right, for x equals 5, right? So again, that's an equation, okay? I just want you to know that. Now, having said that, right, this is the trick to substitution because the question is something like this. And it's no different than solving it with graphing. The question is, if you were to graph it, right, at what point would two lines intersect, right? It's the same thing because we're looking for a solution here. So the question is something like, well, at what point do these two equations, at what point do these equations intersect one another? And this is how you can follow. All right, so let's try it. Okay, so right here, right, we got x equals 5, and the second equation is y equals 2x minus 3. Very straightforward. You see how here the variable's been defined for you, right? The variable's been defined. It says x equals 5, right? So instead of where x is, all you have to do is rewrite, and where x used to be, I'm just going to put the 5 in there, right? So some of you might say, wow, Mr. Sterling, that sounds really like a sixth grade topic. Not wrong. It's just that in the sixth grade, you wouldn't be able to do something like number 5 by using substitution. All right, not to the degree that you can now. So in a way, yeah, this is a very simple example of substitution for systems. Doesn't mean that it's not legitimate. Okay, so 2 times 5 here is 10 plus 3, so that's 7. So now some of you might say, so it's 7. What about it? Right? If x equals 5, y equals 7, that is where this is the point where these two lines will intersect. Right? As a matter of fact, let me get my graphing calculator just to prove that point to you. Okay, so hold on one second. Now, here, let me enter this in. Oh man, x equals 5. I don't can enter x equals 5 on the calculator. That's the problem. Maybe I can show it to you down the line. Okay. Let's go ahead and do number 2, and then I'll prove it to you. Okay. All right. Now, because of space, I need to erase this. Okay. So you need to write this down. You can press pause. I shouldn't erase I want to save some just so that I know I finished the question. I'll use it. Okay, all right, number 2, right? So here we got 2 equations. Now, this is a little bit less straightforward because, as you can see, right, the first one, we defined what x is going to be. So that made it simple. Here it's not so simple, but it's also not very difficult either. Because do you see why? Because this is, they both are y, right? So what you're saying is, and this is like, classical Greek rationale, right? And I'll show it to you right now, all right? All right. Ancient Greek philosophical lesson. If A equals B, and B equals C, what can you say about A and C? Yeah, they're equal, right? So if A equals B and B equals C, then A must equal to C, right? Because they both share one thing in common, which is B, right? So similarly, all right, if y equals to this, so I'm going to show it to you in that Greek fashion, okay? If 3x plus 6 is equal to y, and y is equal to 4x, what can you say about 3x plus 6 and 4x? Yeah, they're equal, right? So therefore, 3x plus 6 is equal to 4x. OMG, what topic is this? Yeah, equations with variables on both sides. Right, so flashback. So here we subtract 6. 4x minus 3x, that's 1x. So x equals 6. Now, here's the thing. That's fantastic. We know that x is going to have to be 6, right? So the x coordinate has to be 6, where the solution is. How do I find out what y is? Simple. You just substitute these in one of these equations. Okay, so I'm going to pick this one because that's the easy one, right? So y is equal to 4x. That means y is equal to 4 times 6. That's 24. By the way, you can use either one because y is going to come out to be 24 no matter what. So that means our point now is therefore 6 comma 24. And that's the solution. Now, if you don't believe me, let's take it to the graphing calculator. Okay, so here I got y equals to 3x plus 6 and 4x. Y equals to 3x plus 6 is 4x. All right, I'm going to graph. Now, the solution is somewhere up there. So what I'm going to do is I'm actually just going to look at the table values. Okay, so I'm going to scroll down. Yeah, look, when x is equal to 6. So look, when x is equal to 6, right? When x is equal to 6, both y values, I was stuck. Both y values, as you can see here, is 24. So we're good there. Okay, so that makes this a solution. So had you graphed this, so let's say if we rewind a week ago, when I asked you for the solution for this, with graphing, you would say this also. Except now we kind of like, we kind of graduated a little bit where we can solve it without graphing. And the method that we use is called substitution. Okay? All right. Let's try one of these together. Let's try 5 together. Oh, now here, same thing, right? Negative 3x plus 4 is equal to 4x minus 10, right? None crazy. Again, equations with variables on both sides. So remember the Pauli method that we talked about early in the year? So this cancels out. 7x minus 10. Add 10 on both sides. Equals 7x. Divide by both sides. X equals 2. Now I got to substitute. Okay. So let's see. I'll just use the second. 4 times 2 minus 10. 4 times 2 is 8. 8 minus 10 is negative 2. So it looks like the solution is 2, negative 2. Now, I can double check. So hold on. Negative 3x plus 6. Negative 3x plus 4. This is equation. Was it 4? No, what is it? 4x? 4x minus 10. 4x minus 10 Wow, it's right there. Look, it's right there. It's 2, -2. So look, 2, -2, right? So they both share -2s for the y value. So I know x is 2. There's our solution. So there you go. Okay. So let's come back to class. Let's practice with the rest of these. Maybe a couple more questions, and tomorrow we'll try some more questions. Okay. All right. I'll see you guys in class. Come on back.
OMG, that was so good.